A presentation on iron carbon equilibrium diagrams. So the subtopics are phase, phase rule, and iron carbon equilibrium diagrams. So myself, M. Kiran Kumar, MTech, CL Mechanical Engineering, Government Polytechnic, Kataram. So now let us have a look of the topics to be covered in this particular presentation. So first one, phase rule. First we need to discuss about phase and then phase rule, then iron carbon equilibrium diagrams. Nothing but initially we'll be moving from the phase diagrams or equilibrium diagrams, then to the iron carbon equilibrium diagrams. So now let us move to the phase. What is a phase? A phase is a homogeneous mixture or a homogeneous portion of a system having a single composition and the same physical and chemical properties throughout its volume. Means throughout the system having a single composition, it should have same physical and chemical properties throughout its volume. That is a phase. So a phase is form of a material having characteristic structure and properties. So it should have or it will have characteristic properties, characteristic structure as well as properties. So more precisely, a form of material with identifiable composition or nothing but the chemistry related with atoms, molecules, bonds, etc. A definable structure either BCC, FCC, etc. Distinctive boundaries or interfaces which separate it from other phases. So now let us move on to a rule given by Gibbs, known as Gibbs phase rule. Which states that P plus F is equal to C plus 2. Now let us know what is P. P is number of phases in a particular system. F is the degrees of freedom, whereas C is number of components in the system. So here we neglect the pressure effect. Whenever we neglect the pressure effect, then the phase rule can be modified or re-given as, it can be given again as P plus F is equal to C plus 1, wherein degrees of freedom are reduced to the temperature and composition. So the next factors concerned to the phase are, phase can be continuous. It may be either a gas, liquid, or solid. It may be a pure substance or a solution, which should have uniform structure throughout. So now let us focus on the phase diagram, or otherwise known as equilibrium diagram. A phase diagram shows the relationship between the composition, temperature, and structure. So a phase diagram is a diagram which relates composition, temperature, and the structure. So it also represents the results of the investigation throughout the solidification process. So whenever the solidification process, what are the stages in the solidification process, we'll be having a observation on the results, investigation on the results. So we can say that the equilibrium or a phase diagram represents the investigation results throughout the solidification process. Phase transformation. Coming to the phase transformation, uh, for a given alloy system can also be given by this, how the one phase to other phase, how the transformation will be occurred, can also be clearly seen in or clearly shown in equilibrium diagram. Phase diagram has temperature on y-axis, nothing but ordinate, and alloy composition as x-axis abscissa. So we can say that x-axis composition, y-axis temperature. Phase diagram can be drawn. So if phase diagrams, commonly these phase diagrams are used for a complete description of alloy constituents. So equilibrium diagrams are also useful in heat treatment and casting operations. So now let us have a look on the different phases, three phases with reference to pressure and temperature. So here on x-axis we are taking temperature in degrees centigrade, whereas on y-axis pressure, nothing but atmospheric pressure. So everything is not given as per the scale, but here let us see, this is 0, this is 100, and here we are taking the pressure as 1. So if we start from here, slightly from 0, this particular phase is a gas or a vapor. Let us start with the first solidification. Whenever it is in the solid form or ice solid form, it changes to liquid water, then vaporizes as a gas. So this is the triple point. So these are the three phases: solid, liquid, and gas phases with reference to the comparison with pressure and temperature. So here, see here, the up to 100 degrees centigrade we are giving, and this is the curve going up, and whereas this is also curve going up. So these are the different phases, how the temperature and pressure varies with the different solid, liquid, and gas phases. Now let us have a sample equilibrium or phase diagram. So this is the composition given on x-axis, nothing but percentage weight, and the temperature on y-axis. So see here at the center half on both sides. So this is the equilibrium or phase diagram. Depending upon the compositions and temperature, this is the line, this is the actual plot we need to get it. So now let us move on to the common types of phase diagrams. Different metals can combine in different ways in a solid as well as in liquid states to give various types of phase diagrams. So depending upon the solubility characteristics of metals, phase diagrams are given as given below. So the first one, isomorphous system, eutectic system, peritectic system, monotectic system, eutectoid system. So if we focus on nickel, copper, isomorphous phase diagram, NiCu isomorphous phase diagram, let us see what happens in isomorphous phase diagram. So composition on x-axis of Cu copper, and this is a nickel, this percentage copper here, but nickel 100 and copper 100. So in between 25, 50, 65, and then 100. So let us see the temperature on the y-axis, T1, T2, and T3, different three temperatures given on y-axis, and the different compositions are given on x-axis. So now let us see here, nickel of 100 to 25 here at a point M, and T2, from T1 to T2 it is solidus, and above M, T33 it is liquidus, and coming to the from 65 to 100 below R it is solidus, and above S it is liquidus or L stage, nothing but the liquid phase. So here we can see the different combinations of liquid plus solid here, and first P, Q, R, S. We need to focus on these points, and M, N, 1, 2, 3. These are the vertical points we need to focus at equilibrium. So now let us see the points. P, Q, R is called solidus line. So here P, Q, R. So this is a solidus line or a curve. POR is liquidus. POR is liquidus. So in this phase diagram, what are the details given or the information given? First is prediction of number of phases. Prediction of number of phases means how many phases are available in this particular component with composition and temperature. Next is prediction of chemical composition of each phase. Prediction of relative amounts of phases. First is how many phases do we have? Second is what is the chemical composition at each and every phase? Third is relative amount of phases. How many prediction of relative amount of phases. So for example, we are considering the copper nickel. If an alloy of 50% copper and 50% nickel is taken as an example, it has only solid phase at temperature T1. So this is the temperature T11. So here it has only solid phase. So a mixture of two phases at temperature T2, that is liquid and solid. Here the T2 temperature is there, and from above liquid and below solid. So a mixture of two phases, that is liquid and solid phases, are available at T2 temperature. Only liquid phase at T3, since it is above liquid line, so that is T3, at temperature T3 only liquid phase is available. So now at points 1 and 3, the chemical composition is same as the composition of alloy, nothing but 50% nickel and 50% copper. At points 2, nothing but 2 here, consider the line T2S, T2 and S. The composition of solid phase is given by points M, that is 25% copper and 75% nickel. Nothing but here 2, T2S. So here T2S we are considering, or the composition of solid phase is given by points M, and here that is 25% copper and 75% nickel. Out of 100%. Similarly, at point N, nothing but the point N indicates liquid phase. So similar to that of the solid phase. So the point N indicates liquid phase, which is 65% copper and 35% nickel. So this is 65% copper at N and remaining 35% nickel. So that is a comparison of M and N. So here, prediction of relative amounts of phases, which is known as lever rule, and at the point 2, percentage of solid can be calculated as length of the tie line on opposite side by total length of the tie line into 100. So length, which is given by 2n, this is the 2n tie line, and the total tie line is mn. 2n is length of the tie line on opposite side, and mn is the total length of the tie line. So percentage of solid can be calculated as length 2n by length mn into 100. So length 2n, so this is 65 minus 50, 65 minus 50 by 65 minus 25, since we are considering m and n. 65 minus 25 into 100, which gives us 37.5%. And if we require the percentage of liquid, we need to subtract this amount from 100. Then we'll be getting the percentage of liquid. So if percentage of solid is 37.5 and percentage of liquid is 100 minus 37.5 gives 62.5%. So we are discussing the phase diagrams. So in the phase diagrams, we are focusing on the isomorphous systems, eutectic system, peritectic system, monotectic system, eutectoid system. So different metals can combine in different ways in a solid as well as liquid states to give various types of phase diagrams. Depending upon the solubility characteristics of metals, these are the different type of systems: isomorphous, eutectic, peritectic, monotectic, and eutectoid systems. So now let us focus on to the isomorphous system, in which the example we are taking is a nickel and copper alloy. So this is the phase diagram of nickel and copper in an isomorphous system. So here nickel, from here 0, 10, 20, 30, 40 up to here taking as 100, and copper 0, 10, 20, 30 up to 100 copper. So this is the temperature and this is the composition: temperature on y-axis, composition on x-axis, and here 50% we are having 1, 2, 3 points, and at 1 we are having temperature T1, and at S we are having temperature T2, and at T3 we are having 3 point. So coming to the nickel copper isomorphous phase diagram. So let us concentrate on the so as we were discussing the nickel copper isomorphous phase diagram. So here we can consider P, Q, R as solidus line or a curve, and POR as a liquidus line. Next, here the prediction of number of phases. The prediction of number of phases. So whatever the information given by this particular phase diagram is, first we can find out or we can predict the number of phases, how many phases occur, and prediction of chemical composition of the phase, and also prediction of relative amounts of phases. So first, prediction of number of phases. So for example, in this particular diagram, 50% of copper and 50% of nickel is observed at a T1 temperature. T1 temperature, both are 50% at T1 temperature, and that is a solid phase. A solid phase is observed at a temperature T1, and a mixture of solid and liquid is observed at T2. So liquid as well as solid. So that is observed at T2 temperature. And only liquid phase is observed at T3 temperature. This is liquid state or liquid phase, that is at T3. So prediction of chemical composition of phases. At points 1 and 3, chemical composition is same as that of the composition of the alloy. Nothing but at 1 and 3, 50% copper and 50% of nickel. Whereas at the point 2, consider T2S. The composition of the solid phase is given by M. So at M, we have 25% of copper, 25% of copper and 75% of nickel at M. And similarly, N indicates liquid phase. So this is the N, where 65% of copper and 35% of nickel are observed. Next is prediction of relative amounts of phases. So this is also known as lever rule, and at point 2, percentage of solid is to be calculated by length of the tie line on the opposite side by total length of the tie line. Length of the tie line on the opposite side means that is 2 and N, whereas the total length of the tie line is given by M and N. So the relation will be changed as 2N by Mn into 100. So length 2N by length Mn into 100, which is equal to length 2N. So 2 and N, so 65 minus 50 by length Mn. So 65 minus 25. So into 100, which gives 37.5%, and this is the percentage of solid available in the phase, and percentage of liquid can be calculated by subtracting the calculated amount from 100, which is 100 minus 37.5 gives 62.5%. So now let us focus on the pure metal and alloy. What is a pure metal and what is an alloy? So coming to the pure metal, only the atoms of one metal are contained in a space lattice. that is pure metal. Whereas a alloy is a substance which consists of two or more elements out of which at least one should be a metal. Nothing but a substance consisting of two or more elements of which at least one is a metal. So coming to the pure metal. So the facts whatever just now we have discussed. Next we are moving to the cooling curve of a pure metal. For a pure metal, how the cooling curve is drawn. So under equilibrium conditions, all metals exhibit a definite melting or freezing point. If the cooling curve is plotted for a pure metal, it will show a horizontal line at the melting or freezing point temperature. So let us see here. So this is the temperature and this is the time. A, B, C and D, 4 points, and at A it is in liquid state and at D it is in solid state. Nothing but from starting point A, whenever it enters A to B, see this is the liquid phase, and B to C and then C to D. So C to D is solid phase, A to B liquid phase, and here in between this is a freezing point. So let us observe the metal from liquid to solid state transformation can be explained in 3 steps. So the first step is removal of superheat from liquid state A to B. From A point to B point, superheat is removed. So whenever the superheat is removed up to B, then from B to C, latent heat is removed at isothermal condition. Removal of latent heat at isothermal condition where liquid and solid states are available. Whereas removal of sensible heat in the solid state, that is from C to D. So removal of superheat A to B, latent heat B to C, C to D is sensible heat removal. So these 3 heats removal changes liquid, changes a component from a substance from liquid to solid state. So here the same graph from A to B where the solidification starts, and at C the solidification ends. So this is the supercooling process. So when pure metals are cooled rapidly, supercooling or formation of solid crystals at the freezing point is sometimes inhibited. So start of solidification is delayed. So here in this particular diagram graph, we're able to see the from liquid state to solidification starting point and solidification ending point and solidification. So this is the temperature range and this is the time range. Now we are moving on to a solid solution. A solid solution is a solution in the solid state consists of 2 kinds of atoms combined in one type of space lattice. Means a solid solution is a solution in solid state consists of 2 kinds of atoms but combined in a single type of space lattice. So it has 2 parts known as solute and solvent. The solute is the minor part of the solution, whereas solvent is the major part of the solution. So now we are moving on to the cooling curve of a solid solution. Solidification of the solution starts at the temperature may be higher or lower than the freezing point of the pure solvent. Most of the solid solutions solidify over a range in a temperature. So from A to B and B to C and C to D. So B to C, phase change temperature starts, and at C, phase change temperature finished. So this above is the liquid phase and the below is the solid phase. So in the cooling curve of a solid solution, the other terms like lower critical temperature, upper critical temperature, melting temperature of alloy A, melting temperature of alloy B are given. So LCT, lower critical temperature, UCT, upper critical temperature, TA, melting temperature of alloy A, TB is given as melting temperature of alloy B. So here, time on x-axis, temperature on y-axis. So A 0, 20, 40, 60, 80, 100, whereas B 0, 20, 40 in the reverse manner, percentages. So starting from the TA, melting temperature of TA to melting temperature of TB, LCT1, UCT1, LCT2, UCT2, LCT3, UCT3, LCT4, UCT4. So lower to upper, this is the curve generated. So here we are discussing the cooling curve of a solid solution. This is the other comparison with the time. This is the composition from 0 to 100, and this is the time given along with the temperature. This is the cooling curve generated. Now we are moving on to a solid solution. A solid solution occurs when we take alloy consists of two metals and they are completely soluble in each other. One should be soluble in other and vice versa. A solid solution is a solution when two metals are soluble one in each other. If a solid solution alloy is viewed under a microscope, only one type of crystal can be seen, just like a pure metal. Solid solution alloys have similar properties to pure metals, but solid solution has greater strength compared with the pure metal. So a solid solution may incorporate into the solvent crystal lattice substitutionally by replacing a solvent particle in the lattice. It can be also done interstitially by fitting into the space between solvent particles. So both of these types of solid solution affect the properties of the material by distorting the crystal lattice. So let us look over the Hume-Rothery rules. There are a set of basic rules which describe the conditions under which an element could dissolve in a metal, forming a solid solution. So, Hume-Rothery rules are the rules which describe the conditions of an element dissolving in the other. So, there are two sets of rules considering substitutional solutions, substitutional solid solutions, and interstitial solid solutions. So for substitutional solid solutions, the Hume-Rothery rules are: the atomic radii of the solute and solvent atoms must differ by not more than 15%. So the relation given here is the percentage difference is radius of solute minus radius of solvent by radius of solvent into 100, which should be less than or equal to 15%. Next rule is the crystal structures of solute and solvent must match. One is the atomic radii of the solute and solvent atoms must differ not more than 15%. And the second is the crystal structures of solute and solvent must match. So this is the diagram as the atoms of the substitutional solid solution. In a substitutional solid solution, the parent or solvent metal are replaced by the substituting atoms of solute metal. See, here blue color atoms are replaced with the solvent of this particular color. So in this case, the atoms of the two metals in the alloy are of almost same size. So this is a substitutional solid solution and the arrangement of atoms. Whereas interstitial solid solution rules. For interstitial solid solutions, the Hume-Rothery rules are as: the solute atoms must be smaller than the pores in the solvent lattice. The solute atoms must be smaller than the pores in the solvent lattice. The solute and solvent should have similar electronegativity. So here, let us see the diagram of interstitial solid solution atoms arrangement. So here, the atoms of the parent or solvent metal are bigger than the atoms of the alloying or solute metal. See, these are the atoms bigger, nothing but the solvent metal or parent metal, whereas the smaller or solute metal atoms. And the title interstitial solid solution is given checking the interstitial space created in between the connecting solvent atoms. So if we consider these four solvent atoms, this is the interstitial space created, and the solute should be such smaller that it should be fit into the interstitial gap of the solvent atoms combination. So that's why this is known as interstitial solid solution. So in this case, the smaller atoms fits into the interstices, that is spaces between the larger atoms. So here a binary phase diagram which is displaying solid solutions. So 100% alpha and 100% beta. This is the solid solution. This is the combination of liquid and solid, and this is above is liquid. This is the temperature. And liquidus and solidus curves compared with the temperature 0, 500, 1000, 1500, 2000, and the compositions are given for nickel and copper in the reverse manner. We consider nickel 0, 20, 40, 60, 80, 100, and copper as 100, 80, 60, 40, 20, 0. This is the graph generated. And this is the other diagram showing the combinations of compositions alpha plus beta, alpha, beta, alpha plus beta, L plus beta, L plus alpha, and above is L, nothing but liquid. This is the temperature. This is 100% A and 100% B. And here a thermal equilibrium diagram is generated, plotted between temperature and percentage composition. Let us see. These are the temperatures 1000, 1100, 1200, 1300, 1400, and 1500. And the percentage of copper are given here as 100, 50, 0, 0, 50, 100 for copper and nickel. And C, this is the above liquid state, solid state, and in between we are getting the liquid and solid phase. So next we need to move on to the chemical compound. A chemical compound is a substance which consists of two or more different elements chemically bonded together in a fixed proportion by mass. So the bond used here is a chemical bond. A chemically combined carbon with iron produce cementite and white cast iron. Cementite, white cast iron are the examples of a chemical compound. So this is the diagram as an example of a chemical compound. Next topic is mechanical mixtures. Two mutually insoluble metal components in solid state will form a mechanical mixture. But the metal components which are insoluble in solid state will form a mechanical mixture. During solidification, these components are separated from melt and form closed mechanical mixture. In iron and carbon system, pearlite and ledabrite are the examples of mechanical mixtures. So with this, we are completing the topics, but let us have a summary of the topics covered till now. Initially, we have started with the phase. What is a phase? We have discussed that a phase is a homogeneous portion of a system having a single composition and the same physical and chemical properties throughout its volume, nothing but throughout the total system. And we have discussed some of the properties of a phase. What are the factors like characteristic structure and properties, and it is a form of material with identifiable composition, nothing but the chemistry, definable structure, distinctive boundaries. So later on, we have moved on to the Gibbs phase rule given by Gibbs. So it states that P plus F is equal to C plus 2. So what is P? P is number of phases in a system. F is degrees of freedom. C is number of components in the system. And if we neglect the pressure effect in the phase rule, then the relation will be changed as P plus F is equal to C plus 1, where in the degrees of freedom are reduced to temperature and composition. Later, we have discussed some of the factors like phase is continuous. It may be either a gas or a liquid or a solidus phase. And it may be a pure substance, or it may be a pure solution, or it may be a whatever it is, but it should be uniform throughout the structure. Later, we have started about equilibrium diagrams, or otherwise known as phase diagrams, which are formed maintaining the relationship between composition, temperature, and structure. Not only that, it represents the results of investigation throughout the solidification process. It also gives the information of phase transformation at different points. So in phase diagram, composition, alloy composition is taken on x-axis and temperature on y-axis. So we have also discussed that the different diagrams with the three phases. So here in this particular diagram, this is a triple point. This is the gas phase, vapor, liquid phase, water, solid phase, ice at pressure and temperature comparison. So this is a sample equilibrium diagram. Composition on x-axis, temperature on y-axis. So this is the equilibrium generated, equilibrium state. So we have also discussed the phase diagram, but phase diagram depends upon certain factors. Depending upon that, those are again subdivided. So depending upon the different ways in solid, different ways of how the different metals are formed, combined. So depending upon the solubility characteristics of metals, also phase diagrams are formed in different systems. So the first system is isomorphous system. Second is eutectic system, peritectic system, monotectic system, and eutectoid system. So later we have concentrated on iron nickel copper isomorphous phase diagram, where we have discussed the solidus line, PQR, POR liquidus line, and some other information for prediction of number of phases, prediction of chemical composition, prediction of relative amounts of phases. So for prediction of number of phases, we have considered at different temperatures what are the different phases available. At T1 solid phase, at T2 at T1 solid phase, at T2 solid as well as liquid, at T3 only liquid state is available. So we also discussed about prediction of chemical composition of phases. So at 1 and 3, at 1 and 3, 50% copper and 50% nickel, and at point 2, nothing but T2S, we can consider M, and at M 25% of copper and 75% of nickel. 25% of copper and 75% of nickel at 2. And similarly, N indicates liquidus line or liquidus phase, where 65% copper and 35% nickel. So prediction of relative amounts of phases known as Lever rule also studied, given by the formula. Percentage of solid is given by length of the tie line on the opposite side by total length of the tie line into 100. Length 2n by length mn into 100. So 2n by mn total length. So 65 minus 50 by 65 minus 25 into 100, we have result is 37.5 percentage. This is the percentage of solid available, and percentage of liquid is obtained by subtracting this 37.5 from 100. That is 62.5% of liquid is available. So later concentrated on pure metal, so which is nothing but the atoms of one metal contained in space lattice, whereas alloy is a substance of two or more elements in which one should be compulsorily a metal. So cooling curve of a pure metal was also discussed. So here from A to B, given by the three steps, A to B superheat is released or removed, and B to C latent heat is removed, and C to D sensible heat is removed. So then whenever we are removing these three heats, it is solidified. So the same process discussed in this diagram also. This is the supercooling area. So solidification starting point and solidification ending point, temperature and time. So this is liquid and starting the solidification. Here the solidification starts and the solidification ends here. This is the temperature range and this is the time. Latter focused on solid solution, which consists of two kinds of atoms combined in one type of space. So it is a solution having solute and solvent, and liquid phase and a solid phase focused on cooling curve of a solid solution having different lower critical temperatures, upper critical temperatures, melting temperature of alloy A Ta, melting temperature of alloy B Tb. So those are the graphs studied. Latter focused on a solid solution. Solid solution occurs when we take two alloys consisting of two metals. They are completely soluble one in each other. So in microscope, whenever we observe a solid solution alloy, only one type of crystal can be seen, just like a pure metal. But compared with the pure metals, solid solution similar properties to pure metals, but with greater strength. Strength will be more. And solid solutions are again divided into interstitial solid solution and substitutional solid solution. So substitutional solid solutions in which the solute may incorporate into the solvent crystal lattice substitutionally by replacing solvent particle in the lattice. Totally the solvent atom is replaced. Whereas in interstitial solid solution, it fits into the gaps of the solvent particles in the interstitial spaces. So Hume-Rothery rules we have discussed for substitutional, having the formula percentage difference R solute minus R solvent by R solvent into 100, which should be less than or equivalent to 15%. That is first rule. Second rule is crystal structures of solute and solvent must match. So these are the solvents and this is the solute inserted of same size. Later interstitial solid solution in which these are the solvent atoms. This is the solutes inserted in between the interstitial space of the solvent atoms. So this is the another binary phase diagram we have discussed. Solid solution below, above liquid solution, in between liquid plus solid. And this is a composition of nickel copper system having 0 to 100 and 100 to 0 nickel and copper compared with 0 to 2000 temperatures. So this is the another diagram explaining alpha and beta. Liquidus, beta, alpha, L plus alpha, L plus beta. So here we were discussing the different cooling curves and entered into the solid solution Hume-Rothery rules for substitutional and interstitial solid solutions. and later nickel copper system we were discussing, and construction of equilibrium diagram, construction of thermal equilibrium diagram. Here let us see, this is the composition of nickel and copper, temperature, and this is the formation of equilibrium diagram, solid, liquid, and in between the equilibrium. So latter focused on a chemical compound. It is a substance consisting of two or more different elements chemically bonded together in a fixed proportion by mass. Latter, we have took an example, mechanical mixtures. Mechanical mixtures are two mutually insoluble metal components in solid state will form a mechanical mixture. So with this, we are concluding this particular presentation. Thank you.